Hey, welcome to Introducing Optimisation. Optimisation, what's that? Maybe we could get a clue from the first part of the word, optimal. Usually means best. So what we're looking at is finding the best scenario, the best solution to some problem. Let's look around the screen now. What's going on here? I think some economists have been busy trying to make a mathematical model for what? The cost of producing perhaps n items a day. And what would be the optimal situation then? Well, we want to know the number of items we produce a day to minimise cost. But then again, let's stay in the economics idea now. What about if they modelled and took the profit we made per day making n items? This time, what do they want? They want the optimal solution is the maximum. So it looks like optimal is an interesting word. It could be the greatest or the least. It's the best scenario in any given problem. Now there are a couple of economic models that we might apply to business. Come on down here. You've seen this one before probably. It's in a lot of textbooks. This one's come from Hayes and Harris, this little picture here. And so what are we trying to do here? Well, what we're trying to do is if we took 150 metres of fencing wire, and we're not going to fence along the brick wall, we're going to start here and go around there, what sort of shape do we make to get the maximum area there? Okay, so we'll say we've introduced x and x here, and if we drew a graph of the value of the area, here it is over here, in square metres for various widths, w metres, well we're going to use x here, then what would we want? We want perhaps a maximum area enclosed. The best solution to this problem, the optimal solution, optimisation, all that stuff, would be that value there, which would be a maximum area. You're starting to get it. What about a pig pen problem? And we're going to do this one later on. If you divide up a certain width here, 1800 metres of fencing wire, and we've got to put in all these different pens here. All these are enclosures. That's an interesting problem. And if we call this x and this y, could we make up a mathematical formula for the area depending upon the size of x there? Okay, and what would we want? Well, we'd want a maximum again, wouldn't we? As we change x, we want to know when the area peaked, when it was a maximum, so the little piggies have as much room as possible. So, are you starting to get the idea of this? Optimisation is getting the best solution, that's all, and it usually means the greatest or the least. Now, I've got to make a little comment here. This is about Year 11 optimisation, and at that level, we're only going to use a bit of technology and some algebra. Later on, optimisation is probably best done with calculus, so you can look forward to that in your future study. Let's go down and have a look at what we're going to do. And look at this. This is a booklet produced by Anthony Harradine and Alastair Lupton. You might have heard of those two guys. Very smart maths teachers, and they've written this booklet to try and help us get our heads around optimisation. One-to-many different situations, greatest and least. I think that's our optimal situation, might be the greatest or the least, depending upon profit or a cost or maximum or minimum area or something. What they got happening here, we're going to look at this in another presentation. They're trying to put a cylinder in a cone. Crazy people. Maybe they want to know what's the biggest size a cylinder they can fit in that cone. And here they got sticking them in spheres, mate, as well. So we're going to come back and look at that mathematical problem. I think they've given you a clue here. You could use a calculator to actually draw a graph of the function. In this case, I think they're looking at the minimum for the optimal. They want the minimum of this thing here. And what's the can doing here? I reckon they got a bit thirsty. Oh, well, maybe not. Maybe it's saying if we have a certain area of tin plate, what's the biggest volume of can we can make? Okay, maximum volume of a can with a given area of tin plate, maybe. Okay, we could lay it out, cut it into a rectangle, wind around, fold it around, make a cylinder, then put the two ends on. That'd be an interesting problem. You might want to play with that yourself later on. Well, enough scribbling. Let's go down and see what these guys got for us in this booklet. Okay, come on down now. And here's our first little problem, the cut straw. We're going to have a straw here. Watch what I'm doing. And it says it's 21 centimetres long. This is not a bad strategy for solving problems. Actually write on the diagram some lengths, and we're going to cut the straw down from the top some distance, and then that bit's going to be laid across the top here. So overall, between that and that, we still have 21 centimetres of straw. Okay, let's look at how they're going to lead us on this journey of optimisation. Optimal, best, finding the best solution. Let's go and have a look now. And here's our first little exercise. Now, what I want you to do is I want you to try to do this yourself. And so what I want you to do now is to pause the presentation and try these two parts. Then I'm going to come along and do it, and you can check your answers with me. We'll do these couple together, and later on I'll let you loose on some of the other ones that these guys have got for us. Okay, pause it now, have a go. Right, well, I'm back. So here we are. The cut is made 6 centimetres from the top. Let's work that out. We've come down 6 centimetres, and the rest is down here. So I reckon the calculation that determines the length of the lower piece of straw, and don't work it out. Well, the whole thing was 21, mate. 21 centimetres. So what are we going to do? The lower piece is equal to 21 take 6 centimetres. Don't work it out, they say. Okay, what about part 2? We have come down 12 centimetres from the top. So there's less down the bottom here. The overall length was 21 centimetres. So this lower bit again is 21 take what we've taken off the top, 21 take 12 centimetres. Okay, what they're doing here, I think, is just training us a bit on how to work with the numbers that we've got, and let's see if we can see a pattern. Okay, did you get it? There you go. Let's go and do the next little exercise they've got for us. Here we are. Now make a T, okay, with the two pieces. So as we said before, we're going to lay it across the top. And consider the triangle formed by the vertices of the T. Let's just rub that out. The vertices are the peaks here of the T shape. Okay, so there's a triangle. That's a bit squishy there. Let's go here. So there's a triangle that we're going to make. Okay, so do you get the idea? This bit has been laid across the top, and now we're going to look at that shape as a triangle. Okay, let's have a look at part B now. Suppose the cut is made 6 centimetres from the top of the straw. Let's draw a picture here. So this is 6 centimetres, and we said before this is 21 take 6 centimetres. Now write down the calculation that would determine the area of this triangle. Do not evaluate it. Well, let's have a look. We said what was left was 21 take 6. Okay. And the base here was the other 6. Oh, hang on, if this is a triangle, okay, you might pause the presentation now and have a go at calculating the area. Do you remember the formula? Okay, pause it, have a go. Right, we're coming back now. Area is a half base times height. So that's a half times the base is 6 times the height is 21 take 6. Do you agree? Did you get that? Okay, now they're going to take us on the same journey of patterning here. Let's see the pattern that might come out in this area calculation. So come on down. Let's go to part 2. Suppose the cut is made 12 centimetres from the top of the straw. Right, before, back in part A. Write down the calculation would determine the area of this triangle. Do not evaluate it. Okay, I'm not going to help you this time. Pause the presentation, have a go, and I'll come back and see if you agree. Alright, I'm back again. So here if the cut is made 12 centimetres down and that's laid across, this one is certainly not the scale now. It would look more like this, wouldn't it? 12, and this was 12 centimetres. This was from before, 21 take 12. And so the area, what you're working, put down good formulas and stuff to show what you're doing. Base is 12 by 21 take 12. Do you agree? Okay, we're building here. And they said don't evaluate this and don't evaluate the whole thing. Let's just look at the pattern that's coming out, because there's some terrific maths coming up in optimisation. What's optimisation? It's just getting the best answer. It's a maximum or minimum. Let's go down and do another one. These guys are taking us on a little trip here, mate. Okay. Suppose the cut is made 18 centimetres from the top of the straw. Write down the calculation that would determine the area of this triangle. Do not evaluate it. Okay, pause the presentation. Have a go. I'll come back. Right, I'm back. Okay, here it is. 18 centimetres has been cut and placed across. So we haven't got much here now. We've got 21 take 18. Okay, and so now the area is a half base times height. Oops, hang on, we'll just stay with little h's there, mate. And here, just remembering what we're doing, it's that area there, so it's a half times 18 times 21 take 18. Are you seeing the pattern that they're trying to show us here? Okay, right, let's go and see what else they've got in store here. Describe what is the same. We'll just get rid of this up here a little bit. Come to the thou, we'll come here. Hang on. Let's just have a look here. Yep, here we are. Describe what is the same, what is different about the three area calculations. Okay, what's the same? The same, what? A half out the front, then some number, and then 21 minus that number. Okay, they all have those features, don't they? Half base times height. The height is 21 minus that number. What is different? Okay, well the only thing that's actually different is this number. The number, hang on, let's just do that differently, because I've got that as same. The actual number varies from part to part. So they're asking us to see, can you see the pattern here of what we're doing? Because if you can see the pattern, maybe we can get a mathematical formula for that. Okay, do you understand that? If something follows a pattern, then you should be able to, using mathematics, find a formula, because a formula describes a pattern, doesn't it? Describes a pattern. Things that always follow the same pattern, we can write a formula for. Okay, well let's go and try and do that. That's where the guys are taking us. So here we go. Let's go down to part D now. Evaluate the area calculations you've written down in part B. As the distance from the top of the straw to the cut increases, what can you say about the area of the triangle? Okay, so I want you to go back and have a look at what you wrote for the three areas and work them out in whatever it is, square centimetres, isn't it? Okay, pause the presentation and have a go. Alright, I'm back. So let's have a look. The first area was a half by 6. 21 take 6 was 15. So that's a half by 6 is 3 times 15 is 45 square centimetres. So that's when you cut off 6 from the top. 6 centimetres. Let's do the next one. Was a half, cutting off 12. 21 take 12 was 9. This gave 54 square centimetres. You might have to do that on the calculator. Oh no, half of 12 is 6. 6 times 9 is 54. And the last one, where we took off 18 centimetres, there's 21 take 18, 3 left. So this is 27 square centimetres. Ooh, what can you say about the area? Okay, can you say something? Well, first of all, it increased and then decreased, didn't it? Okay, so we took off 6 centimetres, then more went to 45, and then if we went to 18, it went down again. So it increased in area and then decreased. So what do you reckon they're going to ask us next? Let's see if we can guess. What's the optimal solution? Optimal area, or maximum area, if you like. I reckon that's what they're going to do. Where in here does the area get to be the greatest? Do you see the question? And we want to do this mathematically, not by trial and error. Well, let's try a bit of trial and error for a start. Let's come down and see what they want to do now. Okay. Write down a calculation for the area of the triangle. Let's start underlining stuff. This is a good problem-solving technique. If the cut is made, any distance from the top, they're going to bring in x. I guess we knew from that patterning, to describe patterns, we probably use a formula. We need symbols in a formula. So let's have a look. What we're going to do now is say, I'm going to cut this down at x. This is algebra. This is good. Algebra to the rescue. When you don't know the value of something, let a pronumeral stand for it. And we usually use x. There's a bit of history to that. Won't go into that. You might Google search. Why do mathematicians in algebra use x? Where did that come from? All right, so here we have it. And then we made this. That was x. This was 21 take x. This was our pattern, wasn't it? Did you see that pattern? And x was 6, and then 12, and then 18. So now the area of this one, let's go through the whole pattern again. Don't get frightened because you haven't got a number there. X is a friendly dude. X will stand for any number. And then you times by 21 take x. Can you see this little dude is following the pattern that we found with our actual numbers? And that's a calculation for the area then. A half x by 21 take x. Okay, do you agree? All right. Let's have a look then at the last one. Use this calculator to generate, with the aid of technology, a table of values. Okay, a table of values for the area. Okay. Do you know, we'll use the Casio 9860 Plus. That's a great little calculator, graphics display calculator. And if you go to table mode, can you do that? See if you can remember how to set up table mode. Okay. Have a go, and I'll show you down here in a minute. So pause it, have a go, and here we are. Down here then is the little bit of work I've been doing. Screen clippings here from the Casio. So we start with finding table mode in there. Hit execute. We go into table function. And it's interesting to know, if you type in, that's what I did, a half times x times 21 take x. This function is also shared across with graph mode. We'll use that a bit later on. Anything you type into table mode is picked up in graph mode as well as a function. So then you've got to hit set, don't you? You remember that? You have to hit set. And it asks you to start with an x value, and I'm going to start with chopping off 1 centimetre and go up to 20. I've made those up. Why would I go up to 20? Could I go any further? Could I go further? And could I go less than 1 centimetre? I think I could. Think about that. Okay, so then if I hit table, it produces a table, and here it is here. It says I'm going up in steps over here. Go back over here. Going up in steps of 1. So I'm going to cut off 1 centimetre, 2 centimetres, 3 centimetres, 4 centimetres. And these are the different area values we get. And we can keep going. I've shown you the end of the table and not the middle there. All right. So that's table mode. Just make sure you look at set first. So you're setting it up as to your starting value, your finishing value, and how many steps there are there. All right, let's go down and see what they've asked us to do with our table. Okay, use your table of values to check your answers to part D. Okay, well, hang on. Have I got it here? What was the first one? 6? Yep. And then we chopped off, what was the next one? 12, I think. Yep, and I haven't gone far enough. You can go down to chopping off 18. And yes, I agree. Find the area of the triangle when x is 7.5. Uh-oh, I can't do it. And I can't do that one either. Why? Look at what I've done. The steps are only steps in 1 centimetre. And we need to go to 0.1. So I have to go back and reset the table so that it's going up in 0.1s. I can answer this one. Yep, when the area of the triangle is 40. Let's see if we can find 40 here. There it is. So I would have to chop off 5 centimetres from the top to make my triangle. Find the value of x for which the area of the triangle is greatest. Well, let's go down. Yeah, not there. It's still going up. Uh-oh, here we go. Oh, there's 2 high values, and then it's going down again, symmetrically on either side. I think we've got it. Somewhere in here would be the maximum area, somewhere between 10 and 11. And because I've only gone up in steps of 1, I can't actually find the actual centimetres there that would give me the maximum. But there we've seen the trend. We said it was going up, and now from that point it's going down. Like we saw before, 5, it was 6, and then 12, then by 18 it was coming down again. So we were picking that up. So to find the value of x, what would we do? Would we guess? I don't think so. We shouldn't guess. We've got to go back and correct the steps, go up in 0.1 or even less to get it more accurately perhaps. Okay, let's go and have a look at that. So here's the table setting. I'm going to change that to 0.1, and we can go up in 0.1s now and get more accurate designation of the areas here, okay, in between. So when x is 14.1, we can get that reading, and we can answer the question in more detail there. Okay, let's go down and have a look. All right. Now, I've gone up in 0.1s, and now where did this come from? What is that? Well, I didn't like trying to go up in 0.1s, 0.01, etc., getting more and more accurate, so I decided to try and make table mode draw a graph. This says graph connecting points. This is a graph plot, not connecting the points, just separate dots for each particular x. But what we want to do is find where in here exactly at that x did we get the maximum area, because this would be area here. This would be amount cut off. So that's not a bad trick. You can have a look at it like that. But the scale is hard to read off here. So we might do it differently. Just before we go from this, what value would it be to go to 0? When would you have 0 area? Think about that. Remember, we're cutting this x down here, and the rest of it is 21 take x. So what 2x values would you have no area? Think about it. It's the area there of this thing. Okay, so when do you have 0 area? When x is what? 0? Yep. And what's the other value x could be so that there's no area for the triangle? I'll just draw it here. Uh-oh. If that collapsed, so x would be the whole 21 centimetres. So this should come down to 0 here at x is 21, where you've taken the whole straw and laid it out and you haven't got any height to your rectangle. So think about those limits here. You could argue that x goes between 0 and 21. Or maybe, if you're a bit more purist, you'd say, well, when it equals 0 or 21, there isn't a triangle. So you might say we go right up to 0 and right up to 21, but not equal. Because if you had equals, no actual triangle exists. The area is 0. So you might like to think about those practical aspects. But the mathematical function can actually have this domain or this set of x values. Okay. Practically, this would be the way we would probably describe it. Alright, well, what about this up here? Finding the exact value of that point, the exact value of the x you have to chop off. Let's have a look down here now. Alright, I've gone to what I promised you before, graph mode. And when I go into graph mode, hit execute there, I find that it's pinched the formula from table mode. It's sitting there for us. And if we hit draw and adjust the view window, we only need to go from 0, don't we, for x? And we've already said probably up to 21. And if we do that, we can actually find this point exactly. Why is that? We'll come over here and let's have a look. If we shift and hit F5, that's G-solve. Can you see it in there? Solving the graph. Now in table mode with G-con and G-plot, you can't actually get it to do this reading off. So once you hit shift and F5 to get G-solve, up come these options, and that's the one we want. The optimal solution here is the maximum area. We're trying to find the biggest area. Okay, so if we hit F2, then we're choosing the max, and the crosshairs sit on that maximum point, and we know when it's exactly 10.5 centimetres chopped off the top, we have this is our maximum area. So just thinking about that, what it's saying is you want to split it perfectly in half. Okay, 21 centimetres split exactly into half. Gives us the biggest area for that triangle. If you want to try and draw something, just adding something here, why don't you draw a series of triangles going up to this scenario and then going down again. Want to try that? Pause the presentation a bit and see if you can see why this half and half will give you the maximum area. Can you picture it? Can you see it? Alright, pause it and have a go, and I'll show you some sketches in a minute. Right, here we go. Let's go and draw some. Just in here before we start the pigpen problem, we'll just maybe go up, come down here a bit. No, we'll go this way. Okay, before we start the pigpen problem, let's have a look at small cuts and keeping most of the straw for the height. That's one. Let's put a larger cut and a smaller height. That's that one. Not to scale here, mate. And then we might go to a bigger cut and let's say the same height. Okay, so these two are 10.5. And then if we keep going the other way, more there and less here. Okay, can you get a feeling? This is not precise mathematics, not scale drawing, but can you see why this sort of fattest one would have the biggest area? Okay, can you see the idea of what we're going through there? Okay, we're going along and getting to the fattest looking triangle, and that's the maximum, then laying it down and squeezing it back again. Okay, some idea there. Alright, these guys, Harradine and Lupton, have got some more problems for us, quite a few in actual fact. Here's the pigpen problem. 3 rectangular pig pens are to be built. They're all the same size. 40 metres of fencing material is available. The area of the pens is important for pig health and well-being. Okay, so again we're going to be looking at area. You get the picture. So we've got 40 metres to make all these divisions, all of them. They've all got to be wired up. Okay, there's the problem. Notice what I've been doing, underlining stuff there, that's important. Okay, and we've got a nice diagram as well, so that's useful. Alright, so let's have a look now at what they want us to do with these. Okay, we're going to find the area. Here's the first little exercise here. If side AD, underline it, is made with 25 metres of fencing wire, write down calculate. So AD is this. That's 2.5 metres. Write down calculations for the amount of fencing material remaining to be used for sides A, B and D, C. So all of these in here are going to be 2.5. Okay, I want you to try to do these three calculations now. Write down the calculations. Don't work it out. What would you do? Right, pause the presentation. Now have a go at those three. I'll come back. Okay, I'm back. So, to be used for sides A, B and D, C. Part 1, well, from the 40, you will take 4 lots of 2.5, won't you? Take away 4 lots of 2.5 from the 40. That's what would be left to do the remaining 2 sides. Okay, what about part 2? The length of AB. Well, 40 take 4 by 2.5 would have to be split into 2, because these two, being rectangular, would be the same. So you're going to split it into 2. I think they're taking us on this patterning journey again. The area of one of the pig pens. Okay, now the area. What's the area? The area of a rectangle is length times breadth. So here, let's actually call this the length. It's 2.5 by this length here. Oh, that's the whole thing. Oh, we only want what? We want 1 pig pen. So let's do the area of the whole thing. This was 40, take 4 by 2.5 over 2. So it's that breadth, 40 take 4 by 2.5 over 2. That'd be the area of the whole thing. And we want to divide it by 3, because there are 3 pig pens. Did you get that? Or did you get caught out and found the area of the whole lot? Remember here it said one of the pig pens. I should have actually circled or underlined that in the problem. Okay, so there's a length, there's a breadth, and we want only 1 pig pen. It's a third of it. So you might not divide by 3. You could have put it this way, 2.5 by a third, like that maybe. Okay, any of that would do. Alright, can you see what we're doing? We're needing to build up our pattern so that we can get a mathematical expression and then see if we can find the optimal solution. In this case, it's going to be the maximum area to find so that we got the maximum health of our pigs. Okay, repeat part A. If 5 metres of fencing is used for side AD. Okay, so this is 5 metres. And so are all of these. Okay, pause the presentation and have a go, and I'll be back. Right, well, I'm back. Okay, here we are. Let's do part 1. What is the length? 40, take 4 lots of 5 now. Okay, and part 2. How long is AB? 40, take 4 lots of 5, and then it's going to be divided by 2. Well, what about the area? The area is length by breadth, which is going to be 5 by, we'll put a third in there, a third of the length, 40, take 4 by 5 over 2. Just remembering, the area is one of these, and this is a third of the whole length of the rectangle there. Okay, I think we're going to be doing this patterning thing again. Let's have another go. Alright, down here in part C. This time 7.5 metres. And we just want 1 pig pen. Pause the presentation and have a go, and I'll be back. Right, I'm back. Here we go. What length have we got left after you do the internal pieces? Like that, haven't we? 40 is the whole amount we started with, and we've got to take off these 4 in here. Okay, and part 2. What's the length of one of these sides? Well, it's what we've got left after doing those internal divisions divided by 2. And again, what's the area? I think you're seeing the pattern. The area is length times breadth, which is 7.5, and we only want a third, so it's a third of that whole length there, which is one of those like that. So there is a pattern emerging. I wonder if you could do it in Xland, bringing in some algebra so that we can see how to find the best solution. And that is, what's the best length you have here to get the maximum area? Optimisation, optimal, best solution, maximum area here. Repeat part A if X metres of fencing is used. Alright, so this is X. Alright. Pause the presentation, have a go, and I'll come back. Alright, here I am, and let's do part 1 again. So it's 40 metres, take 4 times the unknown that we want to chop off to make the maximum area. And we're going to go and find X in a minute. Part 2, what's the length of one of those other sides? 40 take 4x over 2. And then finally the area. Same stuff. Length times breadth, which is the length by a third of one of those sides. Okay. Hey, we've now got a formula which we could generate values for and see the trends in the area as we choose different size lengths for that side of the pig pen. Okay, let's do it and have a look. So, generate a table of values for the area of one of the pig pens when X takes lots of values. Okay, have a go at that and see what you come up with. Okay, pause it and see what's going to happen there. Alright, so come on down. Here we have it. There it is, X times 20 take 2X. Oh, what have I done there? That looks different. But I've actually changed the formula because the area was X times a third of 40 take 4X on 2. Did a little bit of maths here, mate. X times, dividing by 2, you've got to divide into both of them. So it's 20 take 2X, and then I've divided the whole thing by 3. So just put it in slightly differently. You could have well put in 40 take 4x on 2 there and done the same thing. Alright, what am I going to do? I'm going to hit set in table mode, start at chopping off 1 metre and going up to 20 this time. Didn't think too much about that. I left it the same as before with steps of 1. So we're going to get a table now for various lengths there, and you can check your calculation. Oh, I went up to 20 and I found something funny going on. Looks like 20 won't work and some of these others don't work. You're getting a negative area. How can that happen? Something went wrong there. Maybe, did I go too far for X values? How far can I go? How much can I chop off of the 40 metres of fencing? What's the biggest X I can put in there? You might look at the formula, which is, well, use the one that we were using before. If this is 40 take 4x on 2, this top line might give you some idea of how big X can be before it gets silly and gives you negative values. Okay, think about that. We're going to come up to that just right now. Let's have a look. Here it is. What range of values can X take? Okay, stop and think about that formula. And also, I've given you a clue here. Giving you a clue with this table of values. Okay, stop and think, pause it. Right, I'm going to come back now. You can see that when you get to X is 10, in the formula, what have you got? That's okay, but when you put in 10 in place of X in this part of it, you'll get 40 take 40 will be 0. X is 10 is the highest value you can have in there before it doesn't make sense. You get negative area. And practically what is that? Well, you had 40 metres of fencing. If you take 4 lots of 10 off, then you have no fencing left. You can't take more than 4. You can't take 4 lots of a number bigger than 10. You didn't have that many metres to start with. What about the lower limit? What happens to the pen? So you can't go bigger than 10. What's the lower limit? Well, don't chop off any. X could be 0. So mathematically speaking, this formula makes sense with X between 0 and 10. On these ends there are no pig pens, however, on the ends, because if you chop off no X, you've got no width for the pig pens, or no length of the pig pens. So probably this is mathematically what you could put into the formula. So we'd call this the domain, or the set of possible X values for that function. But practically we would go right up to 0, but not include it, because this would be practically the domain to ensure pig pens actually exist if we go right up to those n values. They don't exist if we let X be 0 or 10. There is no actual pig pen. Okay, so did you get that? Start thinking about those things. They're important to solve optimisation problems, to know what range of values are possible, so that you can pick out the best value within that range. Alright, what else have they got in store for us? They've got a couple of other things down here. Use your table of values to find the value of the area calculations you wrote down in parts A to C. Okay, so you have to go back and dress those up a bit. What about this? If the area of one of the pig pens is 15.36, you might have to change the steps now in your table. Go steps of 0.1 or something like that perhaps. Okay, and then the length of AD if the area of one of the pig pens is maximised. Well, what have I done? Well, I bailed on table mode and I've gone to graph mode, as I said before. Use Shift F5 and gone to GSolve. Okay, so here's our graph. See the zeros, and this is at 10. When X is 10, when X is 0, there's 0 area, there's no pig pen, it's flat. And we wanted this point here somewhere. So when we hit Shift F5 GSolve and choose max, the crosshairs pop on and we find the pig pen has maximum area when X is 5 and the area is 16 2/3 square metres. You see that recurring decimal is 2/3, so that would be metres squared. Alright, so suggesting now, rather than try to get down in table mode to smaller and smaller increments to get areas for any X value taken off there or used there, you might go to graph mode. And you can also, of course, in GSolve, you might also find a ycalc for any given X. So if you type in or you hit ycalc on the second window and put in your X, it will give you the area for any X. So you could do it that way as well. Okay, let's go and have a look at the last little bit now. Make a scale drawing of the pig pens when their area is maximised. Let's see what we've found. X was 5 metres. So the other length, the AD, what was that? It was 40 take 4 times X on 2, which is 40 take 20 on 2. 20 on 2 is 10. So actually the pig pen was 5. I'm not drawing this to scale, you were supposed to though. And the other length was there. That was twice as long. That was 10. Okay. So here we had, what are they? 10 metres. This is 5 metres. We had 3 in here. Okay, like this. You've got to draw it accurately to scale. 5 metres. So that's a total of our 40 metres. If you add all those up, you have 40 metres, and that's how we use them. So the pig pens, well, this would be 10 over 3, wouldn't it? 3 1/3 metres. Each of these would be 3 1/3. Okay. 10 over 3, 10 over 3. And if you check one pig pen, the area would be 5 by 10 over 3, and if you work that out, that's 16 2/3 square metres. Okay, so it's an interesting result. The length of the pen, 10 metres, was twice the width there. An interesting result. Okay, and we've used mathematics to find the optimal solution. Optimisation problem. We wanted to find the best, the optimal solution is the best, the maximum or the minimum, and we've just done that. Okay, let's go down and see what else is in store here. There's some more problems for us. So here's a folded page problem. I'm not going to help you with this one. I want you to pause and go through the same things again. Look at this. Can you detect a pattern? And then can you make a mathematical formula for it? Should be able to if there's a pattern. And then go on and work with it. All right, have a go. Pause the presentation. Try to do the whole problem. I'm going to show you the solution in a minute, so pause it. Okay, here's the solution from the publication from Harradine and Lupton. These guys have done well for us here. Okay, how did you go? Check those answers. Okay, study it, go back and correct the pieces. What I'm going to do now is give you another one. They've got some more for us down here. Okay, so here's the swing wing fighter plane. Same thing again. Can you go through and study it? Okay, I want you to pause the presentation. Use underlining to make sure you've used all the values. Mark it on the diagram perhaps. There's one marked on the diagram here. Okay, have a go. Here's the solutions now. Alright, there we have it. Check your answers, see if you can make sense of them, and check them off. Alright, I hope you've enjoyed the journey so far. There's got a little bit more to go, but what have we been doing? I've got some hints for you here, which might help out in optimisation problems. Here they are here. How are these hints for solving optimisation problems? Okay, and we're going to go through these steps using the original straw question. Okay, so carefully read the question, underline key points to avoid missing them out. Draw a diagram, making sure the given information is marked on it. Now, we don't usually go through the trial and error with different numbers to see the pattern. We usually introduce X straight away. These 4 problems that they've given us here, very nice, they're training problems, saying have a look, can you see what's happening? But if we're actually trying to solve an optimisation problem in general, we won't go through those trial and errors. We'll go straight to trying to find, or introducing X and trying to find that missing piece. So let's do it here. Here we are, 21 centimetre straw. We're going to draw it now. And we're going to cut off a bit from the top. Well, here's our diagram. What is the size of the piece which should be cut? So 21 centimetres, cut from the top end and form a T. So I'm going to underline all that. Draw the diagram. Okay, marking on it the information. What size of the piece should be cut? Let X be the size of the piece, and somewhere we should put in centimetres. To produce the maximum area, that's why it's optimisation, the best solution, the biggest or the smallest value. So let's draw this now. We now have this, and we can draw our picture, and we want the area. But now we have to be sure of labelling it properly. That was x chopped off and laid across the top. So this is 21 take x. We're not doing that trial and error stuff that the guy showed us what to do there. So we're down to that. We've introduced a pronumeral. Write down a formula. Oh yeah, we did that before. The area of a triangle is a half base times height, which is a half x times 21 take x. And we're well on the way. We've been able to describe what will happen in all cases of x. Okay, we've got to here now. If there are other quantities involved in the formula, try to write them as expressions in terms of the introduced pronumeral. Oh, well, I already did that. The other quantity was the height. So I realised that had to be 21 minus what we cut off and put across the top. So that's this one. It's important to keep the number of pronumerals or letters for missing quantities down to a minimum. We don't need to call it y, because we knew the total length was 21. Now if we take off the x, we have it all in x land. Just one variable, one unknown, one pronumeral. There it is. So we've got right to the end there, right down to that point. Follow these steps. It might be a good idea after I've finished this to pause the presentation and write down all of these steps because they are useful in optimization work. Okay, using algebra or technology, find the maximum and minimum value as required. And we want, go back up here, it's underlined, we want maximum, and state your answer in the context of the question. Don't state it in X-land. Okay, let's do it now. We've done it with technology, using a graph. What about with algebra? Can you do it with mathematics without any technology? Let's see. Well, the area, let's expand the bracket, is a half x times 21 minus a half x times x. So this is what? 10.5x take a half x squared. Well, we could factorise that, couldn't we? We could say here x outside of 10.5, oops, don't want a bracket in there, take a half by x. Okay, so what could you do there? Well, this is going to have x-intercepts at 0, and when x equals, when you put this equal to 0, get x equals 21. Okay, so let's just come down a bit. So here what we know is the function going to be 0 there and 0 there, and because it's neg x squared, it's going to go something like this. So what's the vertex value? Ooh, the vertex value is halfway between the zeros, isn't it? Symmetry. So x equals 0 plus 21 on 2, the mean, halfway between two numbers, is their mean, and that's 10.5 centimetres. So we could actually do this problem with our knowledge of quadratics, and that's optimisation at this level, or we could use technology as we did before. So we want the size of the piece up the top here, which should be cut 10.5 centimetres. So now state the answer in the context, not x equals. So the 10.5 centimetres should be cut from the end. Okay, a contextual answer, not x equals. They give us a problem in words, the practical problem, then you have to actually give not x, you introduce that to solve the problem. Good use of algebra, finding something missing, let a pronumeral x stand for it, but then at the end of the day, come back into the context of the question. That's important. Alright, do you get it? Please keep Huddy's hints close handy by so you can follow them through. They will always work for you. Okay, we've done each of them. Now, I want to let you loose on some problems. So here we go. The guys have got some more problems for us. Here's the two-pipe problem. I want you to trace through the steps that they're getting you to do and make sure you use those Huddy hints to make up a formula and use technology, or you might like to check it with algebra as well. Okay, pause the presentation, and in a minute I'm going to show you solutions. Right. Here are the solutions. Well, not completely solutions, actually. The answers. Not actually showing you completely how to work it out. That's a difference between an answer and a solution, isn't it? An answer is just what they've asked for. A solution is showing all working. And if you want marks in tests and exams, you have to write solutions in mathematics. Give reasons for your steps. All right. Check your work. And let's go on to the next problem. There's some practice ones here for you. They're good ones. Athletics field. These are meant to be semicircles. The graphics there aren't so good, but they're semicircular ends as explained. So go through the steps. Try to see the set of steps that I want you to do to get into that formula and then to maximise or minimise it. Remember, optimisation just means best. And best is either the greatest or the least. Okay, and they're asking that right down here. Pause the presentation, see how far you can get with this one. Hopefully now you're starting to warm up and you can get some done. Right. Here's the solutions. Here are the solutions. Did you get it right here now? Okay. Have a go. Work through. The most important thing then is, when you introduce the pronumeral, can you get that formula all just with R's in it? And then you can use technology or algebra to find the maximum value. I think there's one more to go for you here. The tin tray. Okay, so think about this. Introduce X, okay, to represent what you're going to cut out or whatever they ask. Okay, underline what they're asking you to find, and then you let X be equal to that and trace it through, pick up the patterns, get a formula, same as before. We have a process now which should stand you in good stead. Alright, have a go. I'm going to show you the solutions now. And here they are. Solutions to that last one. Well, I hope you've got some idea of the power of mathematics now in finding the optimal solution, in optimising and solving optimisation problems. Alright, so I hope you've enjoyed yourself. There's going to be a couple of other presentations on this one, on optimisation. We might go into those 3D problems. How do you stick a cylinder in a sphere and get the maximum volume and stuff like that? So, it's cheers for now. Catch you later on.